back in the assess, page 346. Yeah, 346, question 7 going forward. It says a rectangular block of metal measuring 6 by 8 by 5, all in centimetres, is melted down. Okay, so we've got liquid metal, right. It is recast as spherical ball bearings of diameter 0.9 centimetres. Alright, so big block of metal, melt it down, make lots of small ball bearings of diameter 0.9 of a centimetre. How many ball bearings can be made and how much metal is left over? Right, how many can be made? Well, let's work out the volume of metal we've got to work with first. Okay, so I'm not going to draw the block, am I? I'm just going to do the maths. Volume of metal available is going to be 6 by 8 by 5. So we've got 6 8 is 48 times 5. I'll tell you what, let's grab my notes. Yep, comes to 240 centimetre cubes worth of liquid hot metal. Lovely. Now I'm going to make some, let's go back to yellow, stands out better. I'm going to make some spherical ball bearings and they have a diameter of that. Right, well, lovely. Let's just work out the volume of each ball bearing. Of course, if I know the volume of each ball bearing, I can work out how many of these I can make using that volume of liquid metal. That's all there is to it. Now, volume of a sphere. So V equals 4/3 times pi times radius cubed. Now, if the diameter is 0.9, let me just say, therefore, the radius is going to be 0.45 centimetres. And that's of course ready to substitute back into here. So let's just do that now. That's going to be 4 divided by 3 times 3.14 times 0.45 raised to the power of 3, and that gives us 0.38151. I'm not going to simplify anything just yet. It's going to give me a volume of 0.38151 centimetres cubed worth of solidified spherical metal ball. And now it's merely a question of dividing this number, the available metal, by that number, the volume of each ball bearing, to find how many I'm going to make. So here I go. So number of ball bearings equals, well, let's take all of this, divide by that, and I got an answer of 629 ball bearings. Now the answer book says 628. The reason being is probably they took the answer for pi, sorry, the value of pi to be 3.1415926, etc. In other words, fill up the calculator space with all the decimal places of pi that it can possibly hold, and of course it makes the volume slightly higher. So if this answer is slightly bigger than the one I've calculated, because remember I'm just using pi as 3.14, if this number is slightly bigger, it would go into 240 slightly fewer times. But in terms of the number of whole ball bearings you can make, it's that. And of course, because 629 is different to 628, it will affect the answer to how much metal is left over. Well, I've worked out 600. I need to work out 629 times this, don't I? See what's left over. So back to this. So what's left over? Is going to be my 240 originally started with. I can't change that. Take away 629 lots of 0.38151 centimetre cubes. Don't have to put it in brackets, but it's nicer to separate it in your mind. You don't have to work out this bit first, obviously. Just whack it all into your calculator. So 240 take away 629 lots of this volume of ball bearing would leave me with 0.03 centimetres cubed, which is nothing like the answer at the back of the answer book, again because originally they got 628 ball bearings and therefore they had more leftover metal, etc. Well, that's not a problem. That's what I made it, and I've justified it as because I've taken pi to be 3.14. No one's going to argue with me for doing that, and so the answers are different but the method is exactly the same, and it's perfect. Right, question 8 on the other page, and then we'll stop. Bit involved this question, bit tricky. I'll just chuck this paper away. I'm done with that. Right, question 8. From the top of an 8 centimetre square base pyramid with a height of 10 centimetres, a pyramid of height 6 centimetres is removed. Better just draw it. Square base pyramid, just so we can see what's going on. So square base pyramid. Let's start with a square base first. So I've got one of these, sort of. I start here, and I join to each vertex and get a square base pyramid, sort of. And then I'm going to come across here and chop the top of that. Alright, so at the moment I've got an 8 by 8 pyramid, and it has a height from top to bottom. Let's just change it to red so it stands out. So that height, which is meant to be totally vertical like so, is meant to be how long? 10 centimetres. So if I put here h equals 10 centimetres. Now then I'm going to chop it across the top like that. So this is me chopping it like that, and I'm going to get a little baby one on the side. So this is me trying to draw a baby one on the side. So it's a titchy one, still square base obviously, because I've cut it across there. And let's just go from here to here, from here to here. Oh, it doesn't really show, does it? Anyway, that's the square base pyramid, but it's just that well, this line's gone behind this other line at the front here. Never mind. So what's the maths for this one? I have got I don't know what it is there. Oh, the height is how much? The height is 6. Okay, change to red. So the height of that one from there to there is going to be 6. So let's change it. Right, h equals 6 centimetres. Right, have I drawn it all correctly? So chop it off, you go and become a little baby one, and you get left over with something that looks like this. Let me just draw how it might look now. I mean, so I've got time to do this, so it's not a problem. Right, so I've got really one of these, like that, and I've got another little square at the top that might look a bit like this. Oh, I don't know how it's going to look. I'm guessing, really. So that's like square. Oops. It looks like that. So you go to you, you go to you, you go to you. Do you see what I'm trying to do? I've sort of lopped off the top, and so this little part here is that's been chopped off, and this bottom part is that. Alright, so real rough, isn't it? So we can now do the maths for it. Right, question A, ready to do it now. Again, of course, in the exam you haven't got to draw all this, it's just, you don't have to do it. What a fraction of the volume of the original pyramid, that's that one there, is the volume of the removed pyramid, that's that one there. So it's this volume compared to that volume. Now we can do it all long and difficult and work out the volume of each pyramid and divide one by the other, but we don't need to do that, because look, we know that the linear ratio, which is the clever way to do it, is going to be 6 compared to 8. Okay, height of 6 compared to 10 based upon the height. So 6 compared to 10. So the linear ratio is 6 to 10, and if I simplify it down, I go 3 to 5. That's the linear ratio. And therefore, in order to access the volume ratio, you multiply each part, you raise it all to the power of 3. So volume ratio is going to be 3 to the power of 3 compared with 5 to the power of 3. Of course, that gives us 27 compared with 125. Now we can answer the question. What fraction of the volume of the original pyramid is the volume of the little one? Well, it's going to be 27 over 125. Therefore, there's your final answer. Oh, not 127. My was skipped over to the 125 there. So it's 27 over 125. That's the correct answer. Alright. Now hopefully I can make B fit there. If not, I can just add another page like that and see what happens. Right, let's see what it says. Find the volume of the remaining frustrum of the pyramid, or frustrum. In other words, what is the volume of this monster here? Well, I've got to work out the volume of the two cones and subtract them. That's a bit of a mission, isn't it? Now, what's the formula for the volume of a cone? You may recall that volume equals, and I've forgotten it, a third times the base area times the height. Right, big one. What is the base area? 8 times 8. What is the height? 10. Lovely. Baby one. What is the base area? I don't know times I don't know times 6. So therefore the problem is, first work out the value of the base length of the square base. Alright, so we don't know what it's going to be, you've got to calculate it. Let's just make it fit here, then flip over to the other page to use these quantities. Now I can use ratios again, because look, I've got x compared with 8, because x relates to 8, in the same way that 6 relates to 10, okay? Because obviously if this is an enlargement, if the bigger one is the enlargement of the small one, and it is, because we have similar pyramids now, because they're all drawn from the same common vertex. Therefore I could set up a very simple little calculation like this. So essentially, let's take a look. I can say x over 6 equals 8 divided by 10. Therefore x is going to be 8 divided by 10, take it over and multiply, times 6, or 6 8s are 48, divided by 10, 4.8 centimetres. Therefore this mystery length here is 4.8 centimetres. I'll be using that to work out the base area and hence the volume of the small pyramid. Alright, so we're going to go next door now and do all the calculations, and I'll be flicking page backwards and forwards to get the numbers right. So here we go. Back to yellow. Volume of large pyramid equals a third times the base area, which was 8 by 8. No need to work out the area of the square first. Multiplied by a height of 10. Just check that's correct. 8 by 8 is the base area times 10 height. That's correct as well. So let's just do that. That comes to 213.33 centimetre cubes worth of volume. Now we're going to do the volume of the small cone. Well, it's not a cone, pyramid, sorry. That's going to be a third by 4.8, wasn't it? Times 4.8 times, I think the height was 6. Yep, height of 6. And that comes to, what we got here? 46.08 centimetres cubed. Right, so volume of the frustum is, let's just refresh our minds. Right, so basically if I chop this little one off the top, I'm left with a shape something like that, although that's very badly drawn. Essentially, take away the two numbers, so 213.33, take away the 46.08, and that leaves me with 167.25 centimetre cubes of leftover chopped off pyramid. And that's it. Not very difficult, is it? But except, you don't always expect to have to deal with linear, area and volume ratios. It's an easy way out of things, it really is. It does help to use that. It's very quick, it's very elegant, it's easy, but you've got to spot it. There you go. I made use of the linear ratio there in part A to work out the volume ratio, and therefore the fraction of the small over the bigger volume. I used it to work out the length of the base of the smaller pyramid. So I've got the 4.8 there, which was the base length, and then used it to calculate the two volumes. The volume of the first one was straightforward because all the information was given us there. Here I had to calculate the 4.8 from before, and the 6 was given us there, then just subtract to get the difference. That's all there is to it. And that's it. And that's question 8 done, and 2 questions for the video is enough, I think. And I'll catch you later for the more tricky ones.